Okay, good morning Year 10, Mrs Allbone here. Welcome to your physics lessons this week for the triple content. We're going to be carrying on from what we did last week, where we looked at the parallelogram of forces and the resolution of forces. So today we're going to be looking at moments, levers and gears, and on your screen at the moment are the facts that we're going to be covering in this lesson. Now, as always, I would like you to have a look at these starter questions. So pause the video and have a go at doing those questions. Okay, so my answers are here. Again, pause the video, just check that you've got those questions correct and you're happy with your answers. Okay, so here you can see a diagram of that, and clearly using a much larger screwdriver is going to be make it much more easy to lift the lid. Why is that? Well, it's because it has a much longer handle, so less force is required in order for you to lift the lid of that paint tin. Now we say the screwdriver, the large screwdriver, has a bigger moment, and this is a term that you're going to need to understand. So what do we mean by a moment? Now, a moment is the turning effect of a force. So up till now we've obviously been looking at forces, but we have just looked at forces that are pretty much in a straight line or perpendicular to each other. But now we're looking at forces which are actually causing something to turn, and we call that turning effect a moment. Now you can increase the moment of a force in one of two ways. Either you can increase the size of the force that's doing the turning, or you can increase the distance between the force and the point of rotation. Okay, so we have a equation that you need to be familiar with. In order to work out the moment of a force, you need to multiply the force by the perpendicular distance from the line of action of the force to the pivot. Now, the force is measured in newtons, the distance is measured in meters, and your units of moment are the Newton meter. Newtons and meters multiplied together. Okay, now this is a bit of a mouthful here. What on earth do we mean by the perpendicular distance from the line of action of the force to the pivot point? Well, for that we need to appreciate the line of action of a force. So the line along which a force acts is known as its line of action. So if we just go back to this diagram that we had before, you can see here the force is in this direction here, the direction of that downward arrow. So the line of action of that force is this line here, straight down. That's the line of action of the force. Equally, if we look at another example here we have a claw hammer pulling a nail out of a piece of wood. So the person is pulling on that claw hammer, and so the force is in this direction. So the line of action of the force is this distance here. And that's what we're interested in when we're trying to work out the moment of a force. We need to multiply the force itself by the perpendicular distance between the pivot point and the line of action of the force. So that would be this distance here. Okay, have a go at that example. If we've got a force of 50 newtons exerted on a claw hammer, and that length, the distance between the pivot point and the force, is 0.3 meters, then what would the moment of that force be? Well, quite simply, we just need to multiply those two quantities together. Force of 50 newtons multiplied by that perpendicular distance gives a value of 15 Newton meters. Have a go at working out this one. If the force is 80 newtons and that perpendicular distance is 0.5 meters, then what would the moment be in this situation? Again, quite simply, the force is 80 newtons and the perpendicular distance is 0.5 meters, so our moment is going to be 40 newton meters. The last one, which is a little bit more tricky, if you have somebody pushing down on that pedal with a force of 15 newtons, what will be the moment of that force? Now you should have found your answer is 3 Newton meters. So let's just check how we get that. Clearly we have got a force of 15 newtons, which is here, and then we are interested in the perpendicular distance of the line of action of the force to the pivot point. So the force is here, the line of action of the force is here, and we are interested in the perpendicular distance between the pivot point and the line of action of the force. So it doesn't matter that the force is being applied all the way down here. What we are interested in is the distance between the line of action of the force and the pivot point, and that is 20 centimeters. Note also that that distance has been converted to meters. Okay, I have a past exam question here for you. So I would just like you to take a look at that diagram and work out the moment of that action. So hopefully you have got a value of 360 newtons, 360 Newton meters for that answer. Now let's just explore that a little bit further. So we have the steel bar here, and that's around 1.2 meters long, and we're also told that distance as well, which is 0.8 meters. So this is where it's a little bit confusing for which values should we use. Well, again, just follow the logic through. You have a force of 300 newtons, and if you look at the line of action of that force, you can see it's in this direction. So we're interested in the perpendicular distance between the force, the line of action of the force, and the pivot point, and that's why you need to use 1.2 meters. So you should have multiplied 300 newtons by 1.2 meters to give 360 Newton meters. Okay, so we've already sort of started talking about levers, so let's look at levers in a little bit more detail. So a lever can be used to increase the size of a force acting on an object, or to make the object turn more easily, and we've looked at 2 examples using the screwdriver and looking at the crowbar as well. So in order for a lever to work, we need to apply a force which acts much further from the pivot point compared with the force that has to be overcome. And a good way of illustrating that is to look at something like a bottle opener. So here, if you needed to open the lid on that bottle and you tried to use your fingers by just putting your fingers underneath that lid and trying to pop it off, then that's not going to work. You wouldn't be able to do that. You would have to overcome a huge force in order to lift the lid. So we don't do that. Instead, we would use a bottle opener. And if we use a bottle opener, it means we can apply a much smaller force over here and end up lifting the bottle lid much more easily. And a bottle opener is just a simple lever. So the force that we are applying is much smaller because it's much further from the pivot point than if we were to try and lift it here, which is much closer to the pivot point. So the whole action of moving that bottle opener creates the same moment anywhere along that lever. And you can create that moment in one of two ways. Either applying a very large force at a very small distance from the pivot point, or applying a much smaller force at a much larger distance from the pivot point. They will both create the same moment, and that allows you to lift the lid much more easily. And we say the bottle opener is acting as a force multiplier. We're allowed to apply a small force to generate a much larger force close to the pivot point. Scissors would be another good example of a force multiplier. So here, where you're cutting that string, you need to apply a huge force. We don't do that. Instead, we apply a much smaller force, a much longer distance from the pivot point, and it creates the same moment here and allows us to cut the string with a much smaller force. So if you apply a small force at the handle, a much larger force is applied to the string by the scissors, and your line of action of your force is much greater from the pivot point to where you apply the force than at this point where you need to apply a much greater force at a shorter distance from the pivot point. Okay, I would like you to pause the video, Year 10, and have a go at these two questions. Okay, so these are the answers to the two questions. So we're using a T-bar here to undo a wheel nut. So why is that turning force much greater here at the nut than the turning force applied at the ends of the T-bar? Well, obviously it's because that nut is at a much smaller distance from the pivot point, which is right in the center of the wheel. So here you're having to apply a much greater force over a very tiny distance, compared with here where you're applying a much smaller force over a much larger distance, and that creates the same moment and allows you to undo that nut quite easily. And for your second answer, if we've got the moment of a force should always be less than 4.8 Newton meters, then what's the maximum force on the gear wheel? Well, you need to divide 4.8 Newton meters by 40 millimeters, having first changed it into meters. So you should get an answer of 120 newtons. Okay, the last thing that we need to look at today is gears. Now, like levers, gears can act as force multipliers, but this time they're going to multiply the effect of a turning force. So the screwdriver had the same turning force at the two parts, but here instead the gears have the same force, and you multiply the turning effect or the turning force. So here we have a small gear wheel, and it's being used to turn a larger gear wheel. Now, right at this point here between the two, this is where the force is being exerted. It's an equal and opposite force because these two gears will rotate in opposite directions. But the force will be the same here. And it will be at right angles, at a tangent to the centre of each wheel. So I've tried to draw that in, but that's a little bit difficult to draw. But your force is going to be at right angles here to from the centre of each gear to where the force is being applied. Now you can see that the turning effect on the larger gear here is going to be much greater than the turning effect here, because the same force is acting at this point, but you have got a much smaller distance with this small gear, so that will create a small moment, compared with a much greater moment which is achieved by multiplying the same force by a much bigger perpendicular distance. So the turning effects are different. Okay, have a go at this worked example, year 10. Okay, so you're asked to find the moment of the force for the 10mm wheel and the 20mm wheel. So the key is the fact that the force is going to be the same for both of them. So our moment will be the force times the radius of the gear wheel. So for the 10mm wheel, it's going to be 80 newtons times 0.01 meters, which will be 0.8 newton meters. And the equal but opposite force will act on the 20mm wheel. So again, it's the same force, 80 newtons, multiplied by 0.2 meters, which will give a turning force of 1.6 newton meters. So you can see these gears result in a different force, turning force, but the same force is applied to both. Okay, and then finally, to finish off year 10, I would like you to pause the video and have a go at this past question. Okay, so hopefully you can see this mark scheme alongside the question. For the first part, we have this heavy wooden pole, and that has a weight of 500 newtons. So obviously that's going to be, that will create a moment at this point of rotation, and that's going to be equal to 500 newtons multiplied by the distance of 2.5 meters. Now in this case you've been given the equation. This is an old exam question, and that won't happen in your exams. You will have to know that equation, but you should have got the answer, 1,250 newton meters. So the smallest force needed to lift the end of the pole is going to be smaller than the weight of the pole. So if you think about it, if he's going to lift at this end, which is a long way from this point of rotation, then it means to create the same moment, he is going to have to apply a much smaller force. A reason for your answer, well, that's exactly why, because the force he's applying is a much greater distance than the weight of the heavy wooden pole. How could he increase the moment? Well, he could increase the force which he uses to lift that pole. Okay, year 10. Now that's our lesson for today, and I appreciate it's quite a long lesson, but there is a lot to get through. We have covered everything of the key facts. The only thing we haven't covered really are these this fact here, which says that the total clockwise moments is equal to the total anti-clockwise moments, and we are going to look at that next lesson. So I hope you've enjoyed today's lesson. I appreciate there is a lot going on. Please rewatch the lesson a few times so that you have the information at your fingertips. Email me if you're struggling with anything. Okay, have a good day. Bye-bye.